Hello students, I'm Mr. Ruffler, a high school chemistry teacher, and welcome to the channel. In this series, we're going to be walking through the brand new New York State Chemistry Regents exam, cluster by cluster. This video is video number 4. It's the cluster on waterproof fabric. If you're looking for a different cluster, check the playlist linked in the description below where you'll find step-by-step walkthroughs of the rest of the exam. Let's get started. Alright guys, if you've been watching my videos, you know the first thing I'm going to say is we are going to read the cluster thoroughly, and then we're going to probably have to come back to it and underline. So the accidental development of breathable waterproof fabric. Outdoor enthusiasts and athletes prefer clothing that is breathable and water resistant. A company's quest to make a refrigerant from tetrafluoroethylene, TFE, led to the accidental discovery of a breathable water resistant fabric. The commercial preparation of TFE began with the production of hydrofluoric acid, HF, from calcium fluoride, CaF2, and sulfuric acid, H2SO4. The HF was reacted at a high temperature with chloroform, CHCl3, to produce gaseous TFE. When the TFE was stored overnight under high pressure and low temperature, the bottles unexpectedly became coated with a slippery, non-reactive, powdery substance called polytetrafluoroethylene, also known as PTFE. So maybe you're thinking back to that first state lab where you were working with the plumber's tape, and rightfully so. Anyways, we're going to dive into question 15. Complete the equation representing the production of HF to demonstrate conservation of matter. So right off the bat, there were a lot of substances mentioned, so we need to go back into the passage and figure out how we are making HF. So underlined in blue, it says that we began with the production of hydrofluoric acid from calcium fluoride and sulfuric acid. Okay, so one of the reactants is going to be sulfuric acid, so H2SO4. And then ultimately, we have to figure out what the other product is. You can think, like I could see students saying that they would have CHCl3 be formed. However, there's no carbon on the reactant side, and there's no chlorine on the reactant side, and we should know that we have to show conservation of matter. We can't just spawn elements out of pure air. So we got to figure out what the other product is. All right, so hopefully you can recognize that this is looking a lot like a double replacement reaction. So I would go through and assign oxidation numbers. If we go to our reference table, we can kind of figure out some of those oxidation numbers just based on the periodic locations. So looking at the location of calcium, calcium is a group 2 element with 2 valence electrons, so it will lose those 2 valence electrons. That means it has a +2 charge. Fluorine over here is group 17, so it needs 1 valence electron, so when it gains it, it'll be -1. And if you think about it, -1 times -1 gives you -2. That makes sense because that'll cancel out with 1 calcium's +2. For HF, calcium will be -1, hydrogen will be +1 based on the location. And then for H2SO4, recognize that SO4 is a very common polyatomic ion called sulfate. Each hydrogen is going to be +1, giving you a total of +2. So you can deduce the charge of sulfate to be -2 because you have one of them to cancel out both of those +2s. All right, so with the oxidation states carried into this equation, now we have to figure out how to do the double replacement reaction. So I just like to highlight when I do double replacements. Notice that this H is coming here, and then the F is coming from here. So what we got to do is we need to crisscross calcium +2 and then SO4 -2. Okay, so when you do the crisscross, Ca +2 and SO4 -2, go ahead and crisscross those, and you will get CaSO4. All right, so that is your equation. It doesn't ask you to balance it. Actually, it balances it for you because they put the 2 in front. So you're good to go here. For question 16, it says, which changes would occur as the TFE produced is changed to a liquid? So thinking that this fabric is existing as a solid, we can consider that the electrical attractions between the molecules are pretty strong. Think in a solid, with a few exceptions, your particles are much, much closer together, versus as a liquid, I can draw them with slightly weaker attractions. And just remember, like, the attractions are what's actually holding together all of the particles. So knowing that the liquid will have weaker attractions is kind of key to answering this question. So choice 1 says the distance between the molecules increase, which they do, and the attractive forces increase. They do not. The attractive forces are going to get weaker, right? That's why it's becoming a liquid. Choice number 2 says the distance between the molecules increase, which they do as a liquid, and the attractive forces decrease. That is the correct answer. But looking at the other ones, choice 3 is saying when it's becoming a liquid, the distance between the molecules decrease. That's false. It increases. And then choice 4 says the same thing. All right, moving along. In 1969, Robert Gore was working with heated rods of PTFE, attempting to gently stretch the material. Out of frustration, after a series of failed experiments, he gave the rod of PTFE a sudden hard pull. This led to a rearrangement of the molecules, resulting in expanded PTFE, ePTFE, a new material with many useful physical properties. Clothing that contains ePTFE is composed of at least 2 layers. The outer rain-resistant layer is generally nylon or polyester, which prevents most of the water from penetrating into the inner fabric layers. Spraying the outer layer with durable water repellent makes it more waterproof. Water vapor from sweat moves through the pores of the layer of ePTFE away from the body, allowing cooling to occur. These microscopic pores are less than the 1 micrometer in diameter. Figure 1 on the next page shows the layers of the waterproof fabric. Okay, then it asks you to rank which row ranks the size of a pore in ePTFE, a water droplet, and a water molecule from smallest to largest. Right, so this one, I think you really just have to use some reasoning. If you can remember back from your first lab, or actually it was my first lab, maybe it was not your first lab, where you were playing with the PTFE tape, you know that this is a polymer, which is a really long molecule. Like, for instance, you have a super long carbon chain with lots of fluorines bonded to it. And this chain will go on for thousands and thousands of repeating units. So this is a pretty big molecule, right? When you think of a water molecule, it looks like that. When you think of a water droplet, you think like there's just a lot more water molecules there. Going back to the question, we can find some pretty core information here. It says that water vapor from sweat moves through the pores of the layer of the ePTFE away from the body, allowing it to cool. If water vapor is moving through the pores, we know that water vapor must be smaller than the pores. That would mean that the water molecule has to be the smallest size, because we know that a water molecule is certainly smaller than a water droplet. And the only answer choice that lists water molecules as the smallest size is choice 4. So by default, that's got to be the correct answer. Right, question 18. Which type of molecules in nylon or polyester would optimize the function of the outer material layer? Going back to our passage, we can deduce some information from this, because it says that the outer rain-resistant layer is generally nylon or polyester, which prevents most of the water from penetrating, yada, yada, yada. The key information here is that it is rain-resistant. If it's rain-resistant, that means that the rain is not penetrating it. It's just bouncing off. It's insoluble. So we have to think about our solubility rules here to answer this. Hopefully your teacher taught you a like dissolves like rule. And what that says is that polar and polar compounds are soluble, nonpolar and nonpolar compounds are soluble, and that nonpolar and polar molecules are insoluble. Well, if we don't want the rain to mix with the outer coating on the jacket, we want something that's insoluble used for the jacket. Right? One of those core facts of chemistry that you must know is that water is polar. Right? So if we're going to get this insoluble relationship, that must mean that the nylon or polyester, or at least those particles on nylon or polyester, must be nonpolar. All right, so we can immediately eliminate choices 3 and 4 because that suggests that those molecules would be polar. And we want them to have weak attractions to water. Right? If they're attracting water, then they're being soluble. If they are not attracting water, then they're insoluble. All right, so that's going to be choice 1 for question 18. So that's it for this cluster. If you found this helpful, be sure to like the video and subscribe for more walkthroughs. When you're ready, you can go into the description and you can look at the playlist for all of the June 2026 Regents clusters. Happy studying.